So welcome back everyone. So today now we are going to have the first uh, lecture in quantum chaos by Surbhi. Over to you, Surbhi.
Hi, thanks for inviting me to give this lecture. Right, so let me begin. I will be talking about quantum chaos. And this lecture series is on ADS, quantum chaos in ADS CFD. I will begin the lectures and then Avik will take over. I will start with the CFT parts and some discussion of the chaos bound, and Avik will take over and discuss the holographic aspects. Basically, this is the plan of my lectures. I will begin with an introduction to quantum chaos and its diagnostics. Then we will compute the out-of-time order correlator in a thermal two-dimensional conformal field theory. And the main reference for the second part will be this paper by Roberts and Stanford. And then we will derive the bound on the Lyapunov exponent in thermal quantum systems. And the main reference for that will be this paper by Maldacena, Schenker, and Stanford. Apart from this, I will also discuss some, like in both of these sections, I will also discuss some results related to higher spin CFTs, depending on how much time we have. Then I will also request all the students to ask questions and stop me and ask questions. Okay, so let's begin. So first of all, let's try to understand what is chaos in a semi-classical game of billiards. If in such a system, if like there is a particle starting from somewhere, so there is a, this is the billiards game, and there is a circular like wall separating, adding another kind of layer to, you know, to get chaos in the system. And then if there's a particle starting from somewhere, it can go at late times, it can go somewhere else. Then if there is another particle and it starts very near to the first particle, however, it will just scatter away. And at very late times, the particles will not have any memory of the initial positions. So at late times, no memory of initial positions. And nearby trajectories diverge exponentially. And this is the famous butterfly effect. Now, how would you measure quantum chaos in such a system? So for that, we look at a Poisson bracket of uh, of momentum and position of the particle. So this is the Poisson bracket that we look at. And what this tells us is it gives the dependence of the final position on small changes in initial position. Here Q is the position and P is the momentum. And the square of this Poisson bracket is a classical diagnostic of the butterfly effect. it's the square of this Poisson bracket. Negative minus of that. And this diagnostic, let's just call it some function C, and we will refer to this quite often in the lecture. It grows exponentially at late times with an exponent lambda L. Yeah, so let me just copy this to the next slide.
Surbhi, we have a question.
Yes.
Yeah, Madhu, please.
Yeah. So, hi, Surbhi. I want to understand. So, in this game of billiards that you set up, right? So, I'm just trying to understand what diverging exponentially means, because it looks like the phase space, or at least the positions that are available, are like in a small box. So, what do you mean by diverging exponentially?
It's basically this commutator, the Poisson bracket, the square of the Poisson bracket, it grows as an exponential in time.
This is even if your phase space is like, I'm just trying to think that if the phase space is small, right, in some sense, then when you say exponent at late times exponentially diverging, it doesn't have much room to go, right? So that's what I'm trying to understand.
So this example is of a semi-classical game of billiards, and I think maybe you're thinking of something more classical.
Mm-hmm.
I haven't looked at the original paper, but in some sense, this one has like more access to more of phase space than not.
I see.
And the point is that what diverging exponentially means is that with respect to the original initial position, that is what is meant here. It does not have any memory of, like, if a particle starts very close to another particle's initial position, the final positions of the two particles
are not close by in any sense.
They are not close by, basically, yes. Okay. In any sense, in the sense of the starting initial, the closeness of the starting parameters, like the closeness of the starting points.
Anish also have a question. Anish, please.
Yeah, so one thing that I didn't understand is how exactly is this a semi-classical system? I think it also ties down with what Madhu was asking. If someone not able to see the semi-classical nature.
Yeah, so the semi-classicalness comes in here. We're using this IH bar.
But that's both on the, I mean, it's like an artifact, I feel like.
Yeah, you
in
can
the
say
system, how do I see that it is semi-classical?
Right. I don't exactly remember the details of how to intuitively see it in this system, but the semi-classical comes in from here. The fact that there is some element of quantum, and we are still looking at classical positions and momenta.
I see. So yeah. Then, like what Madhu was asking, that if this the last equation that you've written, that this is if I give the initial position in phase space, if it is always is exponentially diverging, is it? Yeah. I mean, because of the finite nature, at some point they should be close together again, right? At some point, they may not exactly. It's not periodic, but at some point they can become arbitrarily close, right? Isn't that possible?
Right. So I think there are two kind of time scales in the system. I think that's what you want to know. Maybe I don't know if I have that in the lecture today. Yeah. So we will see, like, there are two kinds of time scales. I have not discussed it for this system. So that time is like the dissipation time, in which still the particles could end up close together, but we are just going to consider times which are much more than dissipation times or collision time. And in that regime, they will not come close to, like, there will be no possibility of coming close together. And that is the regime in which the butterfly effect happens.
I see. Okay.
Yeah. I will just discuss the dissipation time in the context of the CFT calculation that we'll do, but maybe I don't have it prepared for this part.
Okay. Good. Actually, we will take just two more quick things before you move on. Okay.
Yeah.
So sure. One is Rohit Kishan is asking over chat that do we have to wait for the late times to see no memory of initial state, or it is a Markovian process where only the last step is remembered? Right. If you want, you can unmute and continue.
Rohit, I just answered that in the previous part, that there is like, it's after dissipation time or collision time that we get the butterfly effect. And the time scale of that is, sorry, yeah, that dissipation time in this particular system goes as 1 over lambda L. And we see the butterfly effect only after this time. Until this time, the quasi-particle picture applies, like, as you were saying, that these are just like classical game of billiards, and it could happen that the two particles could end up close together again.
Yeah,
So
what I actually meant,
right.
what I actually meant was that, like in a Markovian process, you start from a point, and since it's scattering, so basically all it needs to remember the last position and momentum values, right? After that, and the scattering will determine where it will go next, and the particles will forget what happened to Tn-2 state, right?
Mhm.
That is how. So, is there a necessity for us to consider late times? I mean, we can see.
Yeah, I'm not very familiar with Markovian processes, but yes, here we are just considering late times compared to dissipation time.
Okay, so is that late time because you want to see that the path difference that is going on? Uh, does it have something to do with it? I mean, the way you are considering that it goes on exponentially, like
Yes.
so.
Yes. Yes. So the dissipation time is when some kind of a 2-point function. So the dissipation time is that if there was a 2-point function. How do I write that? Yeah. Q. So I don't know if you can understand this in the context of Markovian. I don't know how to explain it in that context, but the dissipation time means that this 2-point function, it goes like some kind of a exponentially decaying function.
Yeah, that makes sense.
Yeah.
In case of Markovian, you only have to do 0 to 1. I mean, t will be replaced by 1. So basically, there will be like back-to-back state, qt
I
and
see.
qt minus 1
Okay.
plus 1. Yeah.
Okay.
Thanks.
Avik. Avik.
Yeah. Just one thing. So in the classical picture itself, do you need to have the square? I mean, in quantum mechanics, I mean, there is some phase cancellation and all these things, but even in classical, why do you need the square?
I think even in the classical, we need the square because of some, in the exponential, I think there are some factors. I'm not very sure of the reason of that. But as far as I remember, we also need the square in the classical.
There's a completely related to that thing. Nehal asked over chat that why did you need to square the pause bracket to make it real? That was the question.
Yes. No, Avik answered that, right? Because of the cancellations in the phase space.
In quantum mechanics, I mean, if you just take expectation value, it may be 0. I mean, just some phase cancellation happens. But if you square it, then it's as a positive definite thing. I mean, otherwise, but I'm not sure why in classical, I mean, that I don't know actually, why you need to do the square.
Here I will also like to clarify, like in this system, the dissipation time is, as I said, it goes as 1 over lambda L, whereas the scrambling time goes as, I think, 1 over lambda L times log of 1 over H cross. So it's like 35 times the dissipation time. So we are just looking at chaos in this window between TD and, so there's a big hierarchy between TD and T star. And we are looking at, we see butterfly effect only after the dissipation time. Fine, so let me continue. And yeah, I jumped ahead and described the scrambling time, but let's continue. Okay. Right. So here we saw this diagnostic of the butterfly effect. I'm sorry, I'm not able to keep track of the chat. So I apologize for that. And
No, that's completely fine. That's my job
Yeah.
now. So yeah.
okay, all right, great. So yeah, as I was saying that this is the Lyapunov exponent. And the scrambling time is defined so the definition of the scrambling time is when this function Ct, it becomes order 1 or significantly large. And in this particular system, the scrambling time is 1 over lambda L log of 1 over h bar. So at this time, the system becomes chaotic and it has lost memory of the initial position. Now this was this so far we just saw a semi-classical system, and next, yes.
This is probably related to what earlier was discussed. So does this kind of, can we interpret that this is like the scrambling time or the dissipation cycle, sorry, the dissipation time of this like length scale or quantum scale that you're interpreting, was that why it's like a semi-classical? That means is it like saying that the scale related to h bar, that initial information is lost or dissipated in this t-start time?
I don't clearly understand the question, but
Well, this t-star, it's a log of a, means I can understand 1 over lambda L, but it's the fact that it's getting this dependence on h bar through this thing.
so because
it
we are
saves some
discussing,
time scale, right? Means
yeah, we're discussing a semi-classical system. That's why there is this h bar here.
yeah. So in that sense, only in terms of scale, it is semi-classical. Otherwise,
Yeah.
we are taking everything.
Yeah, to clarify again, dissipation time is when the quasi-particle picture no longer applies. I don't know if there are people who are familiar with statistical mechanics kind of systems. So there is this word of integrability and non-integrability. So quasi-particle, so this means that the system after TD, after dissipation time, the system is no longer integrable. And after T star, the system has descended into proper chaos. Like it's completely non-integrable. Okay. Yeah.
So this is the scrambling. T star is the scrambling time.
Yes. Yes.
Yeah,
Yeah.
I have a question regarding this. So,
Yeah.
where does the mixing time scenario comes in between dissipation and scrambling time, or scrambling time is the mixing time?
Which scenario? Sorry.
So you just you try to describe this in like statistical integrable systems, right?
Right.
So even in that case, there are this concept of mixing time.
I don't know that. I don't know that. Sorry, I don't know the concept of mixing time. Yeah.
Akhil.
Hi, I have a question. Why is the dissipation time like defined with respect to the Lyapunov exponent again? Like, what's the intuition?
It will come in it comes in the calculation, I think, of the 2-point function. So I don't have an intuition right now, but it comes through the calculation.
Okay, thank you.
Yeah.
Pawan.
So I'm confused about the 1 by h bar inside log. Shouldn't it be dimensionless inside the log?
Yeah, there must be some factors of dimension which I'm not keeping track of.
Right. So okay.
let's
So,
move
so
on.
I'm trying to get a sense of how big this term is, T star. That's why.
Yeah, I mean, can we describe it in a way like T star is the time when finding the probability of finding each of the particles become uniform throughout the phase space? Is it something like that?
So this is the definition, and it actually comes from string theory. The scrambling time was initially defined in some string theory literature. So I don't know how to exactly understand. I mean, I don't know how to answer that question, basically.
Well, I should say one thing. I mean, if you go to the quantum picture, all these definitions are very clear. I think even if Surbhi doesn't, but I will probably discuss it in some amount.
Yeah.
Classically, I don't know how transparent this idea is, but once you go to quantum, then there's a very nice clean picture of scrambling.
Okay, I see.
Sorry, can I interject a little bit? So this mixing time or this scrambling time has some description in terms of phase space. I'll describe it in my lectures. So yeah, so one can understand it classically as well. Yeah.
Thanks.
Excellent. I would suggest to go light the question in Slack as well. So that would be, then we can never forget to ask you in your lectures.
Yeah, it's in my slides. So
sure. Perfect. Banashri, you have a question.
Yeah, hello, Surbhi. So, means my query is, when this Lyapunov exponent is negative, then you can say the system is dissipative, right?
No. It's so here, if you see, I have defined it like this. So there is already a negative here.
So negative Lyapunov exponent
TD,
doesn't mean a dissipative system. My question is that.
No, I don't think so.
Okay.
I don't know if Lyapunov exponent even can be negative.
Means if it is positive, then you can say that the system is chaotic. But if it turns to be negative, then system is, what kind of system we have?
I don't know, and I think it is defined to be a positive quantity as far as I understand.
Confusion. Are you trying to see
initially integrable? It should remain integrable.
Two people are speaking. I cannot hear.
Oh, sorry.
Yeah.
I was just saying that if it was like initially your system is integrable, then if it is your lambda L comes out to be negative, I would think that it is finally also it remains integrable because your nearby points, initial points remain nearby.
Anyway, Surbhi, I think let's move on.
Yeah, I think I'll move on because
please post the question again in Slack.
Yeah,
we have less interaction in Slack anyway, so just put it there. We can
there is a dedicated channel for her lectures. Please feel free to post all your questions.
Perfect. That would be great. Yeah.
Yeah.
Surbhi, please carry.
Yeah. So just a quick recap because some people might have lost track because of the questions. Semi-classical. So this is the diagnostic of chaos. Which grows exponentially with the Lyapunov exponent at late times. So this is late times. And this is the Lyapunov exponent. And for this system, the scrambling time, which I defined as being as the time when this quantity CT becomes order 1. So this is the scrambling time. Now in quantum systems, in quantum mechanics, this Poisson bracket is promoted to a commutator of Hermitian operators. And this commutator, it measures the effect of perturbation. So it measures by perturbation by V on later measurements of W operator. And again, the diagnostic of chaos, the CT is the thermal expectation value of this commutator squared. Where by thermal expectation value, I mean this. Okay. Right. And as I had already mentioned, chaos manifests at late times. And at late times, the expectation value of the commutator square okay, I need one more.
Sorry, I just missed. What was W and V again?
These are some operators in the theory, in the quantum mechanical theory.
I see. They need not be related to P and Q.
Yeah. Right. So then at late times, this becomes like 2 times this just the 2-point function, so the disconnected contribution and the out of time order correlator. This is the out of time order correlator. As you can clearly see why this is said to be the out of time order correlator. There is 0, t, and then 0 again, and then t. So this is the out of time order correlator that is quite discussed in literature recently. Right, and we will now focus only on this correlator because it captures the exponential growth. So this out of time order correlator captures the exponential growth. And we will just focus on this in the remaining lecture. Right. And then, as I was saying before, there are 2 time scales. I have already explained the dissipation time. No longer quasi-particle. And it is determined from the 2-point function. And the 2-point function decays, dissipates exponentially. And this dissipation time is of order beta in thermal systems. Beta is inverse temperature. And then the second is the scrambling time, which I have already described. And in this, for this lecture, for these lectures and for the computations that I'm going to show you, we will focus on the regime when scrambling time is much greater than the dissipation time. And we will always be looking at times also which are much greater than the dissipation time. Right, so I think this will be a good time to ask questions before I move on to the OTOC computation in thermal 2D CFTs.
Excellent. As I don't see any hand raised, so there is a question in the chat that perhaps a very naive question. So Neha, if you want to ask the question directly, you can ask.
Hi. So my question, I don't completely understand if it's a good question, but when you say when you define chaos, you define it as initial trajectories which are very close by have a very large exponential separation at late times, right?
Yes.
So is such kind of a limit well defined when we are talking about quantum or semi-classical regime? Because I naively think that quantum means you talk about small separations.
I mean, again, the thing is that what is small and what is large? You're talking about smallness with respect, I mean, largeness with respect to something. So
Okay.
here I'm talking about largeness with respect to inverse temperature.
Okay.
Yeah.
Pratik, if you want to go.
So you are using a symbol, like, is it the symbol of asymptotics, or how is it defined actually?
This tilde?
Yes, this tilde symbol. Yes.
I think I just mean approximately and yeah, and in this late time regime.
Okay, so in the sense of asymptotics, you have to define after some time. So is it the this T star? Scrambling,
after the dissipation time.
Okay, so this is the okay.
Yeah. Or I can just write this as T much larger than beta.
Okay, I see. Okay.
Yeah.
Semanti?
Hi. Can you explain that quasi-particle thing? I am not understanding. What do you mean by definition of quasi-particle?
Right. So basically, it's when in a quantum system, equations of motion and so basically the quantum system is solvable. You can tell the final position from the knowledge of the initial position and some more data. That is the regime where quasi-part. It's called to be satisfying some kind of a quasi-particle picture, or the system is said to be integrable.
Okay, I guess that's okay for Semanti. Anish, if you want.
Yeah, sorry. So I'm a bit new to this subject. So this C of T that you have written, this chaos, right?
Yes.
So earlier you wrote it in terms of this the square of this Poisson bracket,
Right.
and here you have these two arbitrary operators W and V. So is this? I mean, what exactly is this W and V? Like, if I choose a different pair of operators, will I get a different C, or the C is the same irrespective of what W and V you choose?
It's the same irrespective of the W and V you choose.
I see. So it's a characteristic of the system.
Yes, it's a characteristic of the system. The only dependence on the operators will be on the dimensions of the operator, but the functional form and the exponential growth will not depend on. Yeah.
One question: shouldn't W and V, like you defined QP Poisson bracket, right? So shouldn't W and V be at least canonical, or is that not a restriction?
These are supposed to be Hermitian and if I think unitary operators also. Yeah.
Okay. So they don't have to be like the canonical variables kind of. W and V don't have to have some kind of convention. Okay.
I don't really understand what you mean by that.
Like Q, you took the Poisson bracket of Q and P, right?
Oh, conjugates of each other.
Yeah, conjugates, right. Sorry.
Yeah. No, no, they don't have to be.
Okay.
Also, if you P and W are unitary, then how do you get dissipative behavior?
Yeah, so here, so they are unitary at a given at 0, right? But then there is evolution in time.
Okay, but unitary will remain unitary, right? Otherwise,
yes.
Unless otherwise, I mean, some decay or some dissipation is there.
Right.
So
And here, sorry.
Kind of thing.
What?
Isn't this a bit circular? I mean, you are saying that they will be unitary at time 0 and then it will not be unitary. But at the same time, unitary will remain unitary unless there is some dissipative.
I'm sure that these operators are Hermitian. I have to check about unitarity.
Okay.
Yeah.
Sure. It seems to be we can move on. But let me remind you all of you again, please press or raise your hand before asking questions. Let's not waste time. Surbhi, let's go on. Yeah.
Sorry, just one thing. I mean, so the Nihal something asked about this quantum thing. If you had a quantum system, something small or something. I think he's probably asking that if you're in quantum sense, you do not probably have this h cut 1 to 0 limit, right? Then is the window of exponential growth still there? I mean, because to get the window, I think you had to set h cut to 0, right? To parametrically separate between T star and T dissipation. Now, suppose I do not have such a small parameter in the system, then is there that window for the exponential?
Okay. For dissipation and the scrambling time. Yeah, I'm not sure. I'm not sure because as far as I've seen, the scrambling time is being defined only in quantum systems. Okay, I think I'll move on.
The host is having a question. ST4 host will ask you a question.
Sorry.
Yeah, sure.
So,
Go
sorry,
ahead.
no, with regards to Avik's question, like, I mean, you can have like in a large n system, right? I mean, some sort of parameter, like, the lowest, the time scale is separate is set by 1 over n, right? I mean, isn't that something?
You have some notion of small parameter, then it's fine. Then you have this window for the exponential growth.
Yeah.
What I'm asking is, suppose you do not have a strongly interacting system, but suppose you do not have such a small parameter, then.
In my research for preparing for these lectures, I, for the first time, looked up how this name scrambling time came about, and I see it defined in some string theory literature of 2007 or something. That's how it started, I think, and it was described in the context of black holes. I don't really understand their definition. How they defined it, but I think it's pretty much a concept which came from string theory and maybe not defined for classical chaos. Okay, so yeah, I'll just move on. I don't know how much I'll be able to cover in today's lecture. We will compute the out of time order correlator. Right, just to recap, this is the out of time order correlator. And I think the slides are slow. This is the out of time order correlator. And we will compute this in a thermal two-dimensional conformal field theory. Right, so a thermal two-dimensional conformal field theory is a CFT on a cylinder, as you might have already seen in Shauvik's lectures. This is the space dimension, and the time is periodic. This is the Euclidean time, and that is periodic. We will relate the cylinder to the plane, but first let's recap. So first I will derive a 2-point function. I think this was one of Shauvik's exercises. So sorry, since I didn't see anybody solving it on Slack, I'm going to solve it here. Right. So the vacuum 2-point function you have already seen is something like this. The conformal dimension of these operators is 2 times the holomorphic dimension and the anti-holomorphic holomorphic dimension. and the holomorphic and the anti-holomorphic dimensions are the same. Right. So, but as you might have already seen that to get the thermal 2-point function, we use a map from the cylinder to the plane, which is given as the following. Where x is the coordinate defined on the cylinder as sigma plus I tau, and x bar is sigma minus I tau. There's a similar transformation for z bar. Z is the coordinate on the plane. Now let's look at the thermal 2-point function. Now, if you substitute the transformation, this transformation, then for the 2-point function, you will get, right, I will go through the derivation actually in more detail here, because I don't want to go through this derivation for the 4-point function. Right, so let's look at it in more detail. Now you saw the transformation was this. Tau is, the Euclidean time is related to Lorentzian time as the following. And the locations are, so the locations of the operators are the following. I've taken the second operator to be at 0. So under the transformation, it just goes to Z1 being e to the power 2 pi by beta sigma minus t. And Z2 is 1. Similarly, Z1 bar is so for the thermal 2-point function, we get, I'm suppressing the bars at several places. If it's not clear, just ask me. So that's the thermal 2-point function. And at late times, it grows exponentially. And here you can see that the dissipation time is proportional to beta. And so in the following discussion, we will just look at the T much, much larger than beta regime for the OTOC. Yeah. Then if you have any questions still at this point, it's a good point to ask. Otherwise, I'll move on.
No questions that I can see. Let's see.
Okay, all right. Let's move on. Then we want to compute the out-of-time order correlator. Let's first consider the following Euclidean 4-point function. there are always bars here. So it's like x1, x1 bar, xi, xi bar. But I'm just suppressing the bars in trying to write it fast. So the operator locations, as I mentioned, are at xj equals sigma j plus I tau j. I will describe the prescription to obtain the out-of-time order correlator. So first of all, right, we have this Euclidean time for each of the operators. And we take the real time, where the real time is, so the real time is related to Euclidean time like this. The real time to be shifted by I epsilon. We assign a small imaginary value to real time. Then, keeping the imaginary time fixed, we will increase the real time to the required Lorentzian value. And then the third step of getting the OTOC is that the operators are smeared in real time and imaginary time is taken to 0. And this third step is kind of done in principle, but it's not really done. And for the OTOC, like specifically to get the OTOC, these epsilons related to the operator locations must have the following hierarchy. So that's the prescription to obtain the out-of-time order correlator.
Surbhi, we had a question, so if you want. Rohit?
Yeah, I did not understand the first and second point of the prescription, especially assigning small imaginary time and all. Could you repeat that part?
Yeah, so basically, these are some operator locations, right? So like as you saw for the 2-point function also, I've just put one of the operators at some value sigma and another at some time t. And the other operator I've just taken to be at 0 at the origin. So to this time, I will, you just take this time to be t plus I epsilon or minus I epsilon, whatever the sign has to be minus here. So you take that time to be t minus I epsilon. It's an artifact of the calculation, basically.
Okay, then?
Then that's the first prescription. So you take that to be, oh, I missed the I here. Maybe that's causing the confusion. Yeah. So there's the
okay,
I
okay,
there.
okay. Now it makes sense.
Yeah. Okay, sorry. And then keeping this imaginary time fixed, you just bring the operator to your desired location in time. And by keeping the imaginary time fixed, you have to have this hierarchy between the imaginary times of the 4 operators so that it is out of time ordered, basically.
Yeah, the hierarchy is there to maintain out of time order, right?
Yes.
Okay.
Can I ask a question?
Yeah.
this hierarchy is yes, it is needed, but then does it matter like how you are making the hierarchy? Like is it like epsilon 2 epsilon 3 epsilon 4 epsilon, or like epsilon epsilon square epsilon cube epsilon to the power 4, like kind of thing?
No, it's just these are 4 parameters: epsilon 1, epsilon 2, epsilon 3, epsilon 4, and they have this hierarchy. I didn't understand your question.
What I'm saying that in the end you will take epsilon goes to 0, right? Like all these epsilons
Yes.
are small, right?
Yes.
So now I am saying 2 hierarchies, two parameterization of this hierarchy. For example, this last is 4 epsilon, the second one is 2 epsilon, and the third one is epsilon, and the first one is like half epsilon or something. Like, this epsilon, 2 epsilon, 3 epsilon, and 4 epsilon. Like, so that is one of the kind. And the second kind might be like epsilon to the power 4 is the least one. The epsilon cube is greater than that. Epsilon square is greater than that. I'm just asking, does that depend on this particular choice of this hierarchy, or it is independent of that? The answer
It's independent of that, but epsilon square cannot be greater than epsilon. If epsilon is less
that
than
I'm
1.
not saying. I'm saying epsilon square is less than epsilon. Epsilon cube is less than epsilon
Okay.
square. And epsilon to the power 4 is less
Right.
than
No, it does not depend on how you're taking that to be. Yeah.
Okay.
So just one comment. This statement about the small imaginary time, I mean, this can be of the order of beta itself, right?
I don't think so.
I mean, for example, this is like you are placing over the thermal circle. Where are you placing? So, for example, beta by 2. I mean,
have you used it like in some calculation to be of the order of beta?
Well, people have used it.
Okay.
I mean, it's not so.
Yeah, I think because we do this basically, as I wrote here, we don't really take the imaginary time to 0 in actual calculations. It's like more of an in principle thing.
Yes, that's right.
Yeah.
Strictly
So
it will diverge.
Sorry, I interrupted you. Please continue.
Yeah, so if you strictly take them to 0, then the 4-point function will probably diverge. But I'm a little skeptical about this small imaginary time thing, because it is often people chooses it to be order beta as well. So the small is, I think, a vague word. I think this ordering itself is crucial. It doesn't matter if it's small or what.
Okay, all right.
Anish, if you want to add some comment or question.
I just had a very quick question. So am I interested? I just forgot this, but I mean, am I interested in OTOC in a Euclidean field theory, or am I interested in the OTOC in the Lorentzian field theory? Which one am I primarily interested in? What was my first question?
So the primary interest is the time ordering comes in only in the Lorentzian picture. Euclidean, it does not come in actually. So I'm just starting with the Euclidean correlator, and
I see.
After doing this prescription, we get the Lorentzian out of time ordered correlator.
I see. So roughly speaking, because these epsilons are imaginary in the Euclidean case, so they don't really affect the calculation of the correlator in the Euclidean case.
So
that
basically, normally like this. Okay, I don't know. Maybe I'm answering the wrong question. I didn't understand your question. But when for a 4-point function is usually like defined in terms of blocks and all for the Euclidean correlator, which I'm going to use later. So that's why I stressed that point.
Like there is no time ordering in Euclidean field theory, Anish. Like
yes,
so in order to, and with the time ordering, like causal time ordering only comes for Lorentzian, and the usual idea is that if you know the Euclidean correlator, you can analytically continue to get your Lorentzian correlators with any time ordering. What she is saying is to get the Lorentzian time ordering for out of time ordered correlator. You can
Right.
choose your epsilons in such a way such that you have a time ordered Lorentzian correlator. That's all that she's saying.
I see. Okay. So the last point where it says that the operators are smeared in real time, what exactly does that mean?
Basically, I think, right. So this is, again, I'm saying it's in principle, but this is not really done. So I think smeared, I don't know exactly what it might mean, but it's like the operator is no longer at a point, but it has some kind of a Gaussian wave packet, maybe. That is what it might mean.
I see. Okay.
Yeah.
Okay.
But this step is not never done in calculations, and we just leave the final result with epsilons.
I see. Okay.
Yeah.
Can I just make a comment? Like, I think the ordering thing, I think the right way to think about it is that you have an ordering in the Euclidean, which is decided by these epsilons. So you calculate an ordered correlator in the Euclidean according to epsilons, and then you continue each of the time parameter to different imaginary thing. So, but since your correlator is defined in the Euclidean path integral, so in the correlation you calculate is calculated with the Euclidean time order you prescribed, but then, and it doesn't care about the imaginary part or the Lorentzian time. So so whatever ordering of the Lorentzian time you want, or whatever order in which you want to insert the operators, you arrange the Euclidean time ordering in that order. If that made sense. I mean, I said a long sentence. Sorry.
I don't understand. Well, so what is ordering in Euclidean?
So you're doing a Euclidean path integral, right? So in the path integral, like the whatever operators you insert in the path integral, the correlation function it spits out, comes out in the order in which the time runs in the Euclidean path integral.
But there is no definition of time in Euclidean field theory, right? Because it's of the
tau,
same
right?
signature.
So if you do the path integral, it gives you only the correlations where tau, the operators are arranged in increasing orders of tau. But now you can take that object and separately continue each of the taus to different values of imaginary part or the Lorentzian time. And you don't want your operators to be time ordered in the imaginary part or the Lorentzian part. But since you started with the Euclidean guy, you can always once and for all fix the ordering of the operators in the Euclidean according to its Euclidean time, and then continue to whatever real time you want for each of the operators. So that's what these epsilons are doing. Its epsilons are the Euclidean times, and then you are specifying an ordering of the Euclidean time. So it specifies what order what is the order in which operators are inserted in your correlator. And it doesn't care about what is the imaginary part of the time.
Okay. Can I move on? I think I was given the instructions that after 11, I can not entertain questions and then complete my lecture.
I was thinking in that way. So let's just move on and keep Akhil's question in the Slack. Akhil, you are the host. You have to post it in the Slack. Okay, please.
Right. So now let's compute the out of time ordered correlator. Now that we know the prescription. Right. So the operator locations are the following. And the epsilons, as I already mentioned, are in this order. So let me just draw a picture on the sigma t plane and what the operator locations could look like. sorry, this is just schematic, just to give you an intuition. Sorry, this is D. Then, as I will show in the next slide, this 4-point function will only depend on the cross ratio. So it is essential to compute the cross ratio. And we will use the transformation between the cylinder and the plane. And the cross ratio is the following. You can check this as an exercise by just doing the steps. And similarly for the anti-holomorphic cross ratio, we will just have this difference here. And another limit of the cross ratio that I will already keep ready before doing the computation is at late times, because as you already know that we are interested in this regime of the OTOC. So the cross ratio in this regime is the following. Similarly for the eta bar, and these epsilon tildes are defined like this. Okay, so that's that. And then we will use what you have learned in Shauvik's CFT lecture. You've already seen how a 4-point function is written as an expansion in Virasoro blocks. So the normalized OTOC is just a function of the cross ratios. Thermal, I'm talking about, right. It doesn't have to be the thermal one, but I'll just use the thermal one for the following discussion. The 4-point function, as you've already seen, is written like this as an expansion in blocks. So this is the expansion in Virasoro blocks. And so we are considering CFT with no higher spin current. First, let's just consider such a CFT, except U1 and stress tensor. So then let me just denote this entire combination to be just the OTOC. And that is, I'll separate out the identity block from the rest of the sum. Now this identity block it contains contributions from identity and all its descendants, including the stress tensor. And the stress, so basically stress tensor is a descendant of the identity. Right. And we already saw that when we already saw in this slide that when time is large, eta and eta bar, they go to 0. So if you look at this equation, maybe stare at it for a minute, you will understand that at large times, eta and eta bar, they go to 0. Yeah, I'll just stop in a few minutes and then you can ask the questions. So at late times, eta and eta bar, they go to 0. And this is called the OPE limit when eta times eta bar goes to 0. And it is in this regime, a 4-point function is dominated by the identity block. So the OTOC in this regime, it becomes it just gets contribution from the identity blocks. And now we will need the form of the identity blocks to go do the further calculation. Right, you can ask questions at this point.
Okay. Akhil, you want to ask?
Hi. So I was slightly confused. We are calculating a VW correlator, right?
Yes. So that's what I meant here.
So shouldn't the OP thing also be like that?
So basically, why I did not write this to be VW is that this discussion from here till this point is actually true for any 4-point function and not just the OTOC. Yeah, so that's the thing.
But like when we are doing this calculation for the OTOC, shouldn't is the more convenient thing to do the VW contraction that particular channel, or is it somehow convenient to do this channel?
There is I don't know if there is a channel here, but so if you just take the operator product expansion of VW right. So if you just do the VV operator product expansion and the WW operator product expansion, then you don't get the required result. Basically, that does not capture the correlator that you want.
We should do VW first, and is that what you're saying, or you have written VV first and WW first, right? So I thought it was natural and probably more right.
No. This does not mean that these are coming close together or something. I mean, this is just a 4-point function. I'm not saying anything is coming. I mean, VV are anyways close together, as you already saw the operator locations. But that is not required for any of this discussion.
No, the question is what is close in the Euclidean thing, right? Since we are calculating the thing plus the...
VV is close and WW is close. VV is close to each other and WW is close to each other.
Okay.
Yeah.
I'd like to make a comment. So Surbhi, there is something also called this large in factorization, or in this language, maybe some 1 over
large
C.
C. Right, yeah.
So is that probably somehow related to this factorization?
Large C is, I think I'll use it in the next step when I write out the identity block in the heavy light
I
level.
think the way you're trying to pose it, like this V and the W operators, they initially do not talk to each other, but due to this,
right,
they becomes, I mean, they have a non-trivial commutator and so on, right? Is that
yeah.
I mean, you start with VV, WW.
Yeah, so I'm saying that this discussion, like from this point is just from this point to this point, it's just true for any 4-point function. And right now, VV and WW are close to each other. Now the out of time ordering will come when under time evolution, V and W operator locations come close to each other. That's when we will see the out of time ordering.
Surbhi, you have 15 minutes left. So how much do you want to cover?
Yeah, I think we can just have discussion and I can stop at this point and continue in the next lecture.
Take some questions, right?
Yeah.
Okay. So I will start with I have one question. So you make a comment that tensor is the descendant of identity. I mean, can you just explain it a bit more?
Yeah, I think Shavik is a better person to explain that. Okay. But it's right. It's some yeah, I'm not
from the identity. Is it some trivial statement that one can just go back and...
No, I think it has to like do this action of these kind of operators on the vacuum. I don't have the full explanation basically.
I can got it. Okay.
Yeah.
Shubham. Shavik is just switched on his video. Probably he wants to say something.
Yeah, so all the descendants are made out of modes of the stress tensor, essentially. And the first descendant of the identity, so the state which Surbhi has written over here, L-1, 0, it is a null state. So you can calculate the norm of this and it is 0. Okay. And then L-2 of when it acts on the vacuum, it is a non-trivial descendant. Okay. And this has got a weight 2, like its conformal weight is 2, like the L0 weight is 2. And the stress tensor is also an object which has got weight 2. Right. So L-2 is essentially the stress tensor, yeah, which has got.
Thanks for that. Okay, Shubham, you can go ahead.
Yeah, so my understanding of this chaos, the computation is that like what Surbhi is I just wanted to clarify some of the points that people were asking, is that like she's mapping the OTOC computation to a 0 temperature CFT computation, and the OTOC in the finite temperature like quantum mechanical system is a time ordered thing in the this thing. Like in the previous slide, she had some Lorentzian continuation of the Euclidean 4-point function, right? So it precisely maps to that, and for that this VVWW correlator is enough. Like you do your Euclidean analysis and then you analytically continue using the time. That is all I think that is happening.
Rito Broto, if you want. Rito, are you there?
Yeah. What I was asking is that the fact that at this limit t tending to infinity, the identity blocks dominate. For that, that one couldn't see in the plane, means why did we have to go to the cylinder? I missed that part.
Yeah, we don't have to go to the cylinder for that. This is all true in the plane also. It's true for just a Euclidean correlator. We don't even have to go to like analytically continue to time or even go to the OTOC for this.
Honestly?
Hello?
Yes.
Yeah. So in classical chaos means we always take the Poisson bracket of position and momentum, and we say means it's we get this exponential behavior and say chaos. So in OTOC, do we need to know the form of these operators, or any time evolving operators can give me chaos?
Any Hermitian operators in the theory.
Okay, if the system is chaotic, means any time evolving operator will give me.
Yeah, it will have this behavior. Yes.
Okay.
The out of time ordered correlator will have this exponential behavior.
So we do not need to know the form of these operators.
No, I mean, there will be just some dependence on the operator dimension, but the exponential growth will be irrespective of what is the operator dimension.
Okay.
Yeah.
Okay, thank you.
Shubham, your hand is still raised. Do you want to ask something or no? Okay. So in that case, Surbhi, you have still 10 minutes around left. So
okay. Let's see.
I have a question. Can I ask Arkya?
Sure, go ahead. This is a question answer. So please.
Could you once more explain to me the difference between exchanging the stress tensor and exchanging the identity? Sorry. Or the relation between, I mean, yeah.
Right. I mean, I don't remember exactly, but basically, stress tensor is some kind of a descendant of the identity. I think I don't remember exactly how that goes, square or something is the stress tensor, and it has to do some about, like, it has to do something with this kind of ladder description of the CFT, ladder operator description of the CFT.
So maybe I can say.
Yeah, sure, Vic, yes.
So it's L-2 acting on the vacuum. That's essentially the stress tensor located at 0 acting on the vacuum. So now, So now the statement is that, so this, when you have this V0, it is the identity block. So it captures all the contributions from the vacuum, which is this 0, and the descendants, which are these excitations on top of the vacuum. So while you write this Virasoro block, you have included the stress tensor contribution and all the higher modes, and the higher modes, like say L-3 and or say L-2 squared and so on, those you can always write it as products of the stress tensor or derivatives of the stress tensor or combinations of products and derivatives of the stress tensor. So all that's contained in the identity block comes from these operators.
Say a bit about how it works in the holographic case also, because there I thought you just mediate via the correlator is computed entirely via mediating graviton or something.
Exactly. So the dual of the stress tensor is exactly the graviton in ADS3. So
yeah, but so I thought the identity part is probably dual to some point contact diagram or something, isn't it? Or so I don't see why there was only a graviton mediated part, right? So why is there not? What corresponds to the identity part? Like identity and its descendants, right? So I see the descendant or the stress tensor or the graviton showing up, but what is the identity part of the chaos calculation in the bulk?
Yeah, the identity is just the background itself. I mean, it's just when you have vacuum ADS3, that just corresponds to the identity, and you do not have any graviton excitations on top of it. That's all.
Yeah, I think in the bulk, it is the disconnected. It's just the disconnected contribution.
Yeah,
the disconnected diagram.
When I do the scattering,
Yeah.
I'll talk about this exchanges, the bulk picture.
Excellent. We still have some 6 minutes left. So
yeah, I can continue, but I think this is a good place to stop, because then it will get confusing if I go any further.
Sure.
I just need like some amount of time to do the next part in one go.
Sure. So let's open the floor for any questions now. I mean, don't.
So I was just commenting. So there are probably two assumptions that people all like to put on this WMB. One is like there are some few body operators, and the other is there are some thermal scale operators. I mean, are they really essential?
W? and the V.
Yes, I mean, one is like there's some few body operator in a system of large number of degrees of freedom, and the other is like there's some thermal scale operators. I mean, they change the energy by a small amount. So those are,
yeah, I'm not aware, but I would guess that is this related to locality of the operators? Is
yeah, maybe because this is related to the question that Bonusri was asking. I mean, so can we just take any operator? So the idea is that, as far as I know, so you put any operator in your system, which is, as I say, suppose you have a system of large number of degrees of freedom, and you insert an operator which actually is a few body operator. So it involves some of the degrees of freedom. Okay. So you suppose you insert it at some time t equal to 0. Now what will happen if the system is chaotic and it's strongly interacting? Then the information of that operator will get scrambled among all other degrees of freedom over this scrambling time t scrambling. So now around that time scale, if you put any other operator, which initially suppose have different degrees of freedom, but since now the information of the initial operator is spread among all the degrees of freedom, so now these two operators will manage to have a finite commutator. Okay, so that's my understanding of this. I mean, these operators V and W. Up to that is completely whatever you choose. So there is one, I mean, so for this exponential growth, probably there is one assumption that it needs to be a few body operator in a large number of degrees of system. But I don't know how crucial is that.
Right, I'm not.
Suppose, yeah, I mean, suppose they have an initial overlap, then will you see this exponential behavior or not at late times? I'm not sure. I mean,
the V and the W have overlap with each other.
Yeah, suppose they have an overlap at t equal to 0 itself. Okay.
Ah, okay, okay.
Here the
Yeah,
idea
I think you had asked me this. Yes.
Initially the CT is small, but yeah, after some time it grows to big. That is the exponential region of growth that you get. But suppose you to start off with, they have a finite overlap. Then do you see this exponential growth? That is, yeah, one thing I don't know.
I think I can answer this tomorrow. I don't have an answer, but maybe we can touch upon this tomorrow again after I have done the rest of the calculation, because I think this might be fit there. Like after we do this Lorentzian continuation, right, to the out of time order correlator. So what you're saying is that, I mean, there are some sheets, and what you're saying is that we're already starting on the second sheet, something like that, I think is what your question is related to.
Yeah,
so maybe. Sorry?
I mean, technically it may be that, but.
Yeah. So technically, yeah, I think we can take it up tomorrow, but I don't have an answer to that immediately.
Excellent. So Avik, can you just post that on Slack as well?
Yeah, sure.
Fill the room with questions. Fill the Slack chat box with questions. Excellent. So yeah, Surbhi, if you want, we can then stop recording.
Yeah, that will be great. Yeah.
Shubham?